So we're getting too close to the end of the course. I'm still missing some large pieces of the stories I want to tell you. So I'm going to take Wednesday, as I already told you. I'm going to use it to discuss essentially computational learning theory, some sort of overview of computational learning theory. Of course, it's not going to be and it can't be a complete course, but it's still part of the course. I mean, it's still part of the exam, and I want you to know what I'm talking about also in this class, which is not going to, unfortunately, I'm not going to have an exercise on this, but it's important for me that you understand the concept, so don't miss it. Now, so we are still talking about Shannon's communication model, and I want you to remember this picture. So we have a source of information, and we have a receiver, and we have a channel. And this is really the basic ingredients of what we call point-to-point communication. When there's one source and one receiver, and we're trying to ask what are the fundamental limitations or bounds or constraints on this story of communication. It's a very general question, and it's a little bit surprising that we can actually describe it in relatively simple terms, or a very few functions that really control the whole story. I know that in biology we usually talk about communication, and it has very, very different things, not only biology, psychology, cognitive science, linguistics, whatever. They all have their own version of thinking about communication. But as far as I'm concerned, as far as we are concerned, I mean, at least in information theory, and also I believe in this is really the most fundamental way of thinking about communication. All of these different types of communication, whether it's neurons that send information from one to another, or whether it's language, or whether it's I don't know, any information that is moving from one point to another point in any way, different parts of the brain, actions and sensing, I mean, all those kind of things, wherever information is moved from one place to another, these are the fundamental questions, and this is the fundamental story behind it. So this is, I want to emphasize it because it's not obvious, and it's not even completely accepted by everyone, but I think it's a very important part of the kind of thing that we want you to do in your research. I mean, you're going to study communication, transfer of information from one place to another, everywhere you look. I mean, in the brain, in cognitive science, everywhere. So this is really one of those fundamental questions. And the way we think about it is using the concepts and functions that we developed so far. The source, which I started to call by, it's characterized by a random variable which I call W now. Think about words or world or whatever you want as this W. And this is these are what we call messages. These are the kind of things that we actually want to transmit. Okay? Now, so usually this concept of messages, think about sentences in text or words in text or the object that I see in the world or object that I hear or whatever it is. Yeah. So there are some things out there that are communicated to us. So we assume that this is a source of information which is characterized by some general probability distribution. So the messages are not known to me, okay? I don't know well, I can predict them more or less. I mean, you know what I'm going to say more or less, but not completely. And therefore, there is some uncertainty in the messages before I send them. And as we know, this uncertainty is in some sense completely characterized by one number, which is the entropy. So actually, strictly speaking, we are not talking about one message, because the message is not, I'm not just sending you IID messages usually. I mean, think about words in text or something like this. They are related to each other. So usually what I actually mean by this is actually some sort of a long distribution, W1, W2, actually sends a sequence of many, many messages. And all of them can be related to each other. And the entropy is, in that sense, is the limit of the probability of the log probability of the sequence. Sorry, 1 over the number of messages, because I'm interested in the rate of entropy. So I'm interested in the description of the uncertainty per word. So this is the log of this probability, where I take a very long sequence of messages, but this is obviously going to increase, because the log, even if they are not really IID, but they are there's some new information in every word, this is going to look like a product of a long product of independent or conditionally independent terms, and therefore this is going to grow linearly with n. So I divide it by n. So this is actually what I want to call not an entropy, but the entropy rate. So this is a slight extension of what we mentioned it before. So the source is not characterized by one uncertainty, but actually the uncertainty per symbol or per message. Now, if my messages are sent in some constant rate in time, let's say I say 3 words per second or something like this on average, then the entropy rate can be measured in what we call bits per second. So it's information per time. Okay? But if actually time comes here by the rate of messages, I mean per unit time. So you don't have to think about time explicitly. You can think about uncertainty per message. Okay. Yes.
I missed, I think, why is it multiplication if they're not necessarily?
So as I said, I mean, we are thinking about problems for which this is factorizable. So the probability of the word I, or the message I, is conditioned on some what we call the parents or the environment of I. So we think that we can always write this probability distribution as a long product of each one of the messages conditioned on some of the other messages which may affect it. So let's say if I think about language is our typical information source, so it's always easier to think about it. So every word in a text is not, of course, independent from the other words, although this is a very easy simplifying assumption. So sometimes we call it a bag of words assumption, as if the text is just, independent words. But they are not, of course. So each word, but if I just look at one word, if I know something about its environment, the words before it, the words after it, the sentences, the context of the whole message. So there's some sort of an environment that if I know it, the words become more and more independent. So if I actually assume that this what I call the parents of Wi is actually a finite set, then it's essentially some sort of a Markov chain. So in a Markov chain, each word depends only on the previous one, only the 2 previous one, only the k previous one. So this is a Markov chain in general. If the environment is limited in its complexity, then this is what we call a bounded rank graph or something like this. We can describe it in many ways, but this is what we call factorizable models. Now, this type of models are essentially everything we do. I mean, one way or another, we don't seriously work with models that are not factorizable. If you think about all the models in physics, I don't know, spins in a magnet, or so whenever the Hamiltonian of the system of a lot of particles is actually a sum over, let's say, pairwise interactions or triple interactions or anything like this, it's a factorizable model. Or whenever the language depends only on some finite neighborhood, and so it's a factorizable null, and so on and so forth. So all these models that we usually work with are of this class. And for this class, the log of the probability is going to look like a sum of conditional and independent terms. The simplest one, of course, is the IID, but IID is only a very, very special case. Okay? Remember that, yeah.
You said that the messages are unknown. They're unknown to the receiver.
They're unknown to the receiver, of course. Yeah. Usually, sometimes they're also unknown to the speaker, but that's a different story. But I mean, they're unknown in the sense that before I receive the message, I don't know what's going to be sent. Now, one thing I didn't tell you explicitly, I didn't have time to tell you about entropy rate, so this entropy, but you're going to prove it in an exercise, I hope. Or maybe you did it already. This entropy actually has a very nice interpretation. It's actually the uncertainty of the word at time t, given the message at time t minus 1, and so on. So the entropy rate is the uncertainty of the predictive, what I know now about the next word. There are some technical assumptions here that there's this stationary process, but other than that, I mean, I don't want to get into this technical details. So I assume that the process is the probability of a certain length of words is, you're not going away, I hope. No. So the probability of a certain length of words is independent of where I am in t. So this is supposed to be invariant with respect to t. This is what we mean by stationary. The probability of a certain collection of objects is independent of a shift in time. So this is actually a rather strong assumption, but we almost always assume it. So the probability of seeing a word in a text doesn't depend if I am on Monday or Friday. Or it's actually invariant to shifts in time, which is, of course, not true, but never. It's true in some asymptotic sense for things like language. So if there is stationarity here, then this entropy rate is actually the uncertainty of a prediction. So the entropy rate is actually telling me how much I can guess the next word, let's say in English. And the surprise is, so you know, there are many, many words in English, essentially infinite. I mean, it's unbounded. But the uncertainty, sometimes in the context of language or speech recognition, we actually call it perplexity of the language. The 2 to the uncertainty is essentially the number of options that I have for the next word. So how much do you think it is, on average, in language? So when I say that the entropy of English is about 2 or 3 bits per word, what it means that there are 2 to these 3, let's say, 8 possible options for the next word, more or less. So the uncertainty of the next word is really very small.
Doesn't it depend on how many words come before?
No, so this is converging. That's the meaning of this limit. Eventually it's independent. We're going to converge with this to a number, which means that essentially I don't need to look at infinity. I mean, at some point it's not going to change.
Yeah, so it's 8 only at the limit.
But the limit is I'm getting to the limit very, very quickly in most cases. Which means that if you take 3 words, you are essentially close enough to the answer. I mean, I cannot improve my prediction of the next word if I look at 3 or 30 words. Okay, I get it. It's slow, very slowly improving. Most of the prediction of the next word is coming for the previous 2 or 3 words. You're going to guess it very quickly. So this is converging actually exponentially fast, in some sense. It's not really true. It's converging like a power law. That's why it's actually hard to estimate the entropy of English. But 3 bits is not such a bad estimate, which means that essentially you can always guess what I'm saying pretty well, what I'm going to say. So the uncertainties you have about my next word is on average 1 out of 8 or 10 options. Actually, it's not only about the word. I mean, if you think about the next sentence, so it's the same entropy rate that converts. So how much? So you don't really know my next sentence, but you know more or less what I'm going to say. And actually, when you read the text, even the next paragraph or the next chapter, there's always a lot of prediction that you can make. So the entropy is actually telling me how well I can predict the sequence. And if the sequence is completely predictable, which means I know I don't need to listen to you anymore. I know what you're going to say, which is true for most of the talks or most of the papers in science. I mean, I really know what it is after reading the title or maybe the abstract, and that's it. In most cases, I more or less know what's missing there. So the entropy is telling me essentially if everything is predictable, the entropy rate is 0. So deterministic sequences, things which don't have any uncertainty, this number is going to converge to 0. And if it's 0, I don't need to transmit it because so I don't need anything. I just give you the first few words, and then you guess already what I'm going to say. I don't need to waste any bits in sending you the information. So essentially, what I really if this is it, this is actually what we call sometimes the prediction uncertainty. So even if I have all the words, the previous words, how much I don't know the next word is the entropy of the source. It's the same thing. Now, so this is actually, again, important. So it means that eventually what we need to send through the channel is just the uncertainty in the prediction error. This is what we really need to communicate. Okay, so if you have some sort of prediction, don't send the word. Send only the difference between what you expect, what you can predict, and what I actually said. By the way, this is something I always tell students. I mean, if you read a scientific paper, the best way to do it, it's also the most intelligent way to do it, is to read let's say, the title, the name of the authors. Actually, it's extremely important to read the name of the authors. The fact that they try to hide it from us in some cases is completely stupid, because there's a lot of prior information that I have in the author names, which I don't want to miss. So I know the names, I already expect something. It tells me a lot. Then, of course, I usually look at the let's say, the references. I mean, where is this guy coming from? And in many cases, actually know the papers that I mentioned in the references, or at least know something about them. So this is already giving me a context. Then maybe, if I want, I read the abstract. And then what I usually suggest to do is to try to predict what's in the paper. So think about it. Okay, this is the subject. These are the people who wrote it. And this is where they're coming from. I mean, this is their past references. What would you write? Okay, now you have a prediction. And then try to look for the prediction error. I mean, where is this paper actually surprising you? I mean, try to identify the places which you couldn't predict. And this is really the important part. And in many cases, this is not very much. So it's actually, why is it a good exercise? Because it forces you to think and to try to actually do the research yourself in some sense. I mean, try to see what's going on there. Anyway, so this prediction error is essentially completely characterized by the uncertainty of the entropy. Never read a paper without guessing what's in it, because then you are essentially just a channel. You don't remember anything. So the channel is the next piece of the story, has essentially inputs and outputs. So let's call these inputs X and outputs Y. And as I said, I mean, this channel is usually a physical thing. I mean, it's something like the air between us, between my mouth and your ear, or the whole complex nervous system that is between my ideas and your perception of the ideas. Whatever happens in between is a channel, and so on. So it can be a very complicated thing. And what we call the alphabet of the channel, the symbols, so both X and Y have some alphabets, some symbols that I'm using. They can be of the same nature, like bits, or letters in an alphabet, or spikes, but they can be of different nature. This can be bits and this can be spikes, or this can be colors and this can be a neural activity, or whatever. I mean, I don't care. X and Y don't have to be of the same nature as well. Okay? But what is important is the channel actually is transmitting information, in the sense that there's some connection, there's some correlation, there's some statistical dependency between the output and the input. Okay? So I assume that the channel is characterized, so there's some conditional distribution of how the output of the channel depends on the input of the channel. Okay? And so we have these two things. We have an information source and someone who is trying to receive my information. And in between there are those channels, which actually can be many channels, it can be a cascade of channels, and can be parallel and serial, and everything. Very, very complicated thing. But they're all characterized by this conditional distribution. And actually, at this point, and in this course, I'm only going to talk about the simplest possible channels, which we call memoryless channels. So memoryless channel means the channel itself doesn't remember anything. You put something in the input, and eventually, after maybe some delay, you get the output, and that's it. This input is now forgotten for the channel. So it's really just like a pipe, you know. You push things in, you get things out, nothing is left inside. So this is what we call memoryless channels. Memoryless channels. Not all channels are memoryless. I mean, the channel can have internal states, you know, like the brain, or things like this. And when I say something, it's actually changing the state of the channel. Okay? So these are much more complicated channels, if they have memory, if they remember things from time to time. And they can have many other things that can be. But so now I'm talking about the simplest possible, the point-to-point, simplest possible mode of communication. So the channel is memoryless, and this distribution is fixed in time. Which means for all times, when I put something in the channel, I get something out of the channel immediately after some delay, but it's the output of this sequence, and each of those symbols, or whatever I put in the channel, is decoded, and that's it. Then it's left the channel. It's not there anymore. Okay? Now, I already told you that, so we already know that the source can be compressed, which means I can encode it with what we call source coding, surprisingly. And source coding is essentially turn the messages of the source to be as compact as you can. Okay, and of course, if I do coding, as you know, source coding is essentially turning my messages into random bits or random symbols. So after source coding, there's no structure in my message. It looks completely random if I do it well, or almost random. I already told you that actually source coding is a non-trivial thing. I mean, if I could actually do perfect source coding of English, I could generate any message any text in English by random sequences. Now, this would be a very smart thing, but I don't have a perfect coding of English because of that. Okay, but if I have source coding, I need source decoding. And of course, if the source is if the code is uniquely decodable, then I zip and unzip, and I get the same message without any distortion and without any loss of structure. Okay? No, but this is what we call lossless coding. I mean, actually, in reality, most really interesting codes are not like that. I mean, they're lossy. But okay, so I'll come back to this question of distortion soon enough. But then the idea of Shannon was, okay, so let's separate the coding into two problems. One of them is the source coding, compress as much as you can, and the source decoding. Sorry, I still have my phone here. It's not mine. Yeah, okay. So essentially, the idea of Shannon is, which is really a very important idea, is to separate. So in principle, I should compress the signal, then transfer it to a channel, and then So, but we actually separate them into what we call source coding and channel coding. And again, channel decoding. And the purpose of these two things is apparently at first it looks very different. Here I want to compress my source as much as possible to the shortest possible description, because I want to transfer through the channel the fewer number of symbols. So there is a hidden assumption here that sending symbols through the channel is an expensive thing. It has a cost. Of course, when I actually communicate, I use energy. I mean, I need to generate this sound wave, which is important. So there are two things that I want to save. I want to save total energy that is going through the channel, or I want to send, in other words, the number of symbols that are actually sent through the channel per unit time. So the rate of symbols that actually sent through the channel is going to be important. I mean, I want to minimize it. Okay? So there is a rate of communication. After compression, there is a rate of bits that comes from the source. Now, if the source has no entropy, this rate is 0. I don't need to send anything. But I know that the minimal rate is this entropy rate. Okay? So in order to send English, I need something like 3 bits per word. This is huge compression, by the way. I mean, usually you have a lot more than that. I mean, the number of bits to actually type English is something like 50 bits per word. So I can compress it quite a lot. Now, the channel is noisy. That's the main point about channels. What I mean noisy? It's not a one-to-one map from X to Y in most cases. So there's some dependencies, but it's not one-to-one. So what characterizes the channel? So I already told you last time. Just like the entropy is characterizing the source, the channel is characterized by something which we call the capacity of the channel, which is the maximum over all possible of input distributions of the mutual information between X and Y. And this has units of bits per second as well. I mean, so because I'm looking at each time frame. So essentially what we should think about here is something very similar to the entropy rate. So essentially you should think about the limit of n goes to infinity of log p of y1 to yn given x1 to xn divided by p of y1 to yn. So I know this looks a little complicated, and I have to take a 1 over n here. But this limit, so essentially I'm thinking about very long sequences. So I'm sending a long sequence, I get out a long sequence in some rate, and I want to see how much my received sequence is different from what I could think without saying C. This is essentially, as you know, this is the mutual information. And this is precisely the maximum over P of X of IXY. And this is information rate. Again.
Should I have a P of X1 to Xn?
Yes.
No, in the definition of the
Okay, so here I use the fact that it's a memoryless channel. And essentially I'm telling you, okay, this factorizes.
Oh, yeah.
So this is actually a pi of pi yi given xi. And then this factorizes. So this is why this is essentially this. By the way, if the channel has memory, or if I encoding a block, this doesn't factorize that easily. I need to keep some whatever is left in my memory, and it's going to affect my prediction. Okay, so for memoryless, this is the memoryless assumption.
The capacity is the same as the information?
No, so the capacity is the maximum possible information rate over the input distribution. Okay? Okay, so this characterizes the channel. this capacity. It's one number. Remember, we took this very general, huge problem of communication and to transfer it into two characteristic numbers. One is the entropy source, and the other one is the channel capacity. Both of them are actually measured in bits per second. Okay? Now, the main result here, which is called the channel theorem, the channel coding theorem, again, this is one of those celebrated results of Shannon from his seminal paper in 48, and then the mathematical theory of communication. So essentially, characterizing the source was one part of the story. This is what we call source coding. And characterizing the channel, so why is the channel capacity so important? So essentially, yeah, the problem is that there's noise here. So originally, before Shannon, people thought that if there's noise, there's noise. There's no way I can recover it completely. They always thought about, taking picture like photocopies, If you take a document and you use an old type non-digital copier, so it's going to deteriorate. So the next copy is going to be noisier than samurai. But after a few copies, you don't see anything. Okay, but the digital communication, which is essentially a direct result of Shannon's theory, is that if you encode it with bits, you can copy as many times as you want without any deterioration. So essentially, you can recover the noise completely. So there's something very important in this idea of encoding it in digital symbols. Now, and this was completely non-intuitive at the time. You can't overestimate the importance of this, or the novelty of this idea in 1948. Now, because everybody was living in an analog world and everything was deteriorating when you copy it and nothing could store it perfectly and so on and so forth. It's not true. As we all know today, we can store not only documents but images and videos and audio and whatever perfectly. Copy it as many times as you want, as long as you're not talking about quantum communication. That's a different story. Now, so what is the condition for me to be able to recover the noise completely and to correct the errors completely? So this essentially is an error-correcting type of error-correcting code. This is the notion that stands behind it. So this code, the channel code, is error-correcting, and so it's able to somehow, wrap the message, the compressed message, with some other bits, which will eventually allow me to correct the errors. That's again a very, very important idea. The fact, and the theorem is essentially an existence theorem. It tells me if the rate of information. So this entropy rate, let me just call it also R. Okay. So R is the entropy rate. Yeah. So if R is less or equal C, the channel capacity, so which means the number of bits that I want to send through the message, the channel is less than the capacity of the channel, the probability of error so essentially I should think about it. Okay, so there is a message W here, and then after all this process there is a received message on the other side, and the question is whether I actually received the correct message. So the probability of error is the probability that W hat is not W. Okay, so that's a very crude estimate. I need to quantify it much better. But if you didn't receive the correct message, then there's an error in the communication. Okay, so this is the probability that W hat is not W is the error probability, or the error rate, sometimes called it actually, because we look at the entropy of this probability or something like this. So if R is then the probability of errors, which is this probability that W hat is different from W in general, on average, or what is the probability that I'm making a mistake in my communication, so I didn't receive the correct message, which of course happens all the time in real communication. So the probability of errors can go to 0 if n is large enough. Or there exists, actually I have to say it much more carefully. It's a complex theorem. In order to prove it, to formally state it, I need many, many conditions. So there exists a code such that the probability of error goes to 0 when asymptotically, when I use large enough blocks. So n is essentially the block size, and how many messages I'm going to encode together. So this is an incredible result because it tells me, okay, as long as your rate is less than the capacity of the channel, eventually you can recover my messages perfectly. And actually the converse is also true. If you are transmitting information in a rate which is larger than the capacity, then essentially the probability of error goes to 1, eventually. Which means maybe some here and there you can hear something, but overall you're not going to miss everything. So I'm not going to prove, certainly not completely, not rigorously, the theorem, because it's. But I want to give you an intuition why it's true. I mean, it's really proving it in the more general cases, hundreds of pages, and I don't want. And actually, there are so many different conditions we still. But that's a very general statement. So remember, now, before I prove it, I actually want to generalize it slightly. It actually took 10 years, or even more, from 1948 to 1959, more or less, 59, 60, to actually reveal to us the whole theory, which is a slightly more general form of this. So, okay, so the story of communication is you compress by source coding, then you add something to the code, which is essentially an error-correcting code. So you're actually getting, again, redundancy into the code. So you add a few bits to the code. It can be a lot of bits, which are those parity checks and all these kind of things that we do in order to error-correct. And then I can transmit it through the channel and recover my original, through this channel coding, which is essentially correcting the errors of the channel. At this point, I get, again, the compressed message. And then I simply uncompress and read. Okay? So this was, at this point, lossless communication. I don't want to lose anything. If you compress a text, you want to see the text. You don't want to lose any bits of the images or the fonts or whatever. But in reality, especially when we talk about analog things like voice or like video or images, maybe we can compress, we lose a little bit. You know, when you use your telephones, your cell phones, you do it all the time. So there's voice coming in, the voice is compressed significantly. So in order to actually sample my voice losslessly, so let's say that my sound has 5 kilohertz of information that I want to preserve, then I need to sample it in twice the rate, which is the Nyquist frequency, which is 10,000 bits per second, 10,000 samples per second. Each sample is, let's say, 10 bits. So in order to actually preserve my voice reliably, I need something like 100,000 bits per second. You know what is the rate of communication in let's say, cell phones in terms of bits per second? Any guess? 2. No. 2 is not even good for text. But no, so something between 5 to 10,000, more or less, bits per second. So if I'm willing to compromise on quality, I can get even to below 1,000 bits per second. Okay, so it's a factor of 100 compression. Or the same is true about images. If you take a picture, megapixel, let's say, of each one, let's say 10 bits, so 3 bits or 4 bits, whatever number of colors you want to use, 8 bits. This is something like megabits times 8 bits, so it's 8 million bits in a pixel, in an image, of only one megapixel. I usually have much more now. So do you know how much I can compress it? So let's say JPEG or something like this. Anybody knows? How much you compress in JPEG an image. So you take a megabit times, so 8 megabits, and you compress them to 10K, 15K, 20K, even less. So this is something you do all the time. I mean, when you compress the images on your phone or your computer, or when you save speech or video. You know how much you compress video? I mean, video is okay.
But 10K is with plus.
Sorry? Yeah.
10K is with plus.
With loss, yeah. So usually this is not a lossless compression. Yeah. So what do I mean by lossy compression? So lossy compression is a very important thing. I'm just going to give you the gist of it. So imagine that I don't really care about reconstructing the word perfectly. So I care about reconstructing it within some what I call distortion. So it can be, the JPEG image is not exactly the original image. You hardly notice it, maybe, if it's a good compression. But sometimes you do see all these glitches in compression. I mean, you see all these things which are not precisely correct. You can even see it with your own eye. But if you actually overlay the two images, you see there are many, many differences. Especially when you look at each pixel, or each bit of each pixel. So there's a lossy compression here. So I replace this, the probability of error, with something much softer. So instead of probability of error, probability of receiving it exactly, which is something which is only well defined for discrete symbols and so on, I replace it with the probability that my distortion between the original message and the received message is not too big. Okay, and this is a distortion function. Okay. Yeah, so there exists some distortion function. That's an assumption, which means I can actually measure how close these two things. For example, the Euclidean distance between the pixels, which is a really bad distortion function. I mean, it's not really what I want. But let's say the Euclidean distance between the images, or between the pieces of voice, or between the text, or whatever, embedded in some dimension, in some Euclidean space. So a distortion function, a natural one, is like this. I mean, you look at the voice as a vector in very high dimension, Euclidean space, and you look at the distance between them, Euclidean, L1, L2, whatever you think is important. I'm not going to get into this, but actually this is a very significant part of my own work. I mean, to justify a distortion function, but in principle we assume that such a thing exists, and then instead of just comparing the entropy of the source, we actually ask what is the entropy, or how much I can compress my source with some distortion. Okay, so obviously if I allow some distortion, the entropy rate should go down, because I need less bits. I mean, this is obvious. So instead of the entropy rate being just the entropy of the source, I look at this function. What is the rate that I need, at a given distortion level? Once again, I'm compressing here a huge subject into a few sentences, but I don't have any choice. So this is called the rate. How would you call it? Oh, it's called the rate distortion function. The rate distortion function. Okay, function. Yeah. And this rate distortion function looks like this usually. So here is the distortion. How much I'm willing to distort my source. And here is the rate. So the rate is the minimum number of bits per second that I need to send if I want to recover my message with some distortion. Now, when the distortion is very small, let's say 0, so intuitively, if the distortion function is 0 when these two are identical, that's what we mean by this, then what is it, the rate? The entropy. Okay, some of you are listening. Okay, it's fine. So, and then it's going down. So here is the entropy, then it's usually, I can prove that it's a monotonically decreasing convex function. Then it's below the strings. Okay, so it's the second derivative is negative. It's monotonically decreasing, and this function is called the rate distortion function. Now, any rate above this line this is what we call the achievable region. These points on the line have the minimum rate at a given distortion. So for any distortion, this is the minimum rate. So this rate distortion is the minimum rate, which is okay. I'm going to write it. Is the information between x and w. The minimum possible rate such that the distortion, the average distortion, is less than d. And this is essentially how the rate distortion function is defined. So I'm looking at the rate of the source and the rate of the input to the channel, and I'm asking what is the minimum number of bits that I need in order to actually transmit these messages with this distortion. Okay, so this is how it's actually a result I need to prove, but this is the minimum rate. And you know that I is going to be just h, that's the entropy. So remember, this is hx minus hx given w, or hw minus hw given x, in this case. And so if this is a deterministic function, this is just the entropy. If this is mapped to one word, then I can actually recover it. So without any loss, I'm actually completely here. So this is the entropy. It's bounded by the entropy of both x and w, and this is going to be h. This is going to be h of w here.
Is it omega hat or omega?
It's w first of all,
Yeah.
and it's the source. Yeah, it's the words. It's how much I can.
But if it's lossless, then.
Yeah, you're right. I mean, the assumption here is the channel is lossless.
Yeah.
So this lossy information is the information that I'm going to lose eventually. It's how much I can reduce the rate of the source without losing, without having more distortion than I'm allowed.
X and W are variables before.
Yeah. I actually cheated a little bit just to simplify things. So there's something here which is called the rate, the distorted coding. So I go from some W to W star or W hat, and then I transmit W hat. But I simply don't have the time now. I'm already beyond the 1 hour. So I simplify things. It's correct what I said, but it needs some explanation. So it's the rate in the channel of the messages. So essentially, this is how many used bits in the channel I actually send in order to obtain a certain distortion. So I do two things here. I take the messages, I compress them such that eventually the rate is going to be lower than the capacity. And this compression is lossy in the sense that I allow some distortion on my message.
So the distortion is due to the coding and not the channel.
Now, the distortion is already done in the decoding. You're absolutely right that eventually what I care about is the distortion between W hat and W. But my assumption here is that the channel is not going to add distortion.
So we're not talking about lossless code now.
No, it's not lossless code. Right. Yeah. This is what we call lossy compression or loss, and this is precisely what we do in JPEG, in MPEG, in all these things that you use all the time. It's a lossy compression. Okay, I have to take a break. But remember this rate distortion function. So there is this function, rate as a given distortion. So I'm going to extend this theorem to a lossy communication. So it's that the rate of the channel, the rate distortion function, the rate of the channel with some distortion is less than E. But then I'm going to add just one more element, and then I'm going to take a break. Imagine there's actually a cost in the channel, like a cost in energy, or a cost in some metabolic cost in communication in neural systems, or some, I don't know, latency. I mean, there can be many different costs. So energy, for example, is a very common one. I mean, how much energy I need in order to transmit through this channel. And obviously, there's some sort of relationship between the cost and the capacity. So what do you think it is? I mean, if I allow more energy or more cost, it's more expensive, I can get higher capacity. This is usually the case. So there's another function here, which is the capacity at a given cost. This also turned out to be very important, again, for neuroscience and for many other applications of these things. So I'm going to replace the rate with the rate at a given distortion and the capacity at a given cost. And this is the most general type of the theorem. Okay, let me take a break here. Continue in 10 minutes or so. אני אוכל כבר. זה אני תעשית את התוכנית. Yeah, no, you don't think about words now. Think about images, or think about speech, or whatever.
Okay.
Yeah. So here I am sending a piece of speech, a piece of music, or whatever.
Okay.
And then I get it here.
Okay.
And I'm allowing a little distortion.
Okay.
Okay.
Yeah. Then what's X? X is the.
X is the code. It's encoded in symbols of the channel of the speech.
So this W is the original.
Yeah, this is the original message.
Yeah, okay.
And this is the code of this. These are the symbols of the channel, and somewhere in between I have to translate the message into sequences of the code.
Okay.
Okay? So I know if you hear it for the first time, it's very abstract, but eventually you'll get used to it.
בהתחלה בזה שהאירור שלי זה כיוון כאילו מנה רסיבר לסור שלי. אז האירור הזה נובע גם כקריטריות בקודינג וגם בצ'אנל. אבל עכשיו הגדרת את זה רק בצ'אנל.
אתה נעד בצודק. זה מה שעושים. זה מה שקראת separation theorem. לא נניח שאני יכול קודם כל לנקות את הצ'אנל.
אוקיי, אז ניסינו למקרה שכל הרעש
נכון. אני עושה הפרדה בשתי השאלות.
אז זה לא נהר.
אני אמרתי את זה, אמרתי מהר.
זה שמעת.
אני מפריד את השאלות האלה. אני עושה מה שנקרא separation. אני קודם דוחס ואחר כך מתקן שגיאות. וההנחה של שנון שאפשר לתקן את השגיאות בלי קשר לסורס.
כן, זה בסדר.
וזה לא תמיד נכון. מה שאתה מדבר עליו זה מה שנקרא joint source channel כזה. שאני לוקח את הרעש של השירות, המשפט היסודי של שנון בעניין הזה שאם אין לי memories, אז ההפרדה תמיד אפשרית. כלומר, אני תמיד יכול להשיג את האופטימום על ידי הפרדה. אבל במציאות אנחנו תמיד בעצם משתמשים בצ'אנל חלק מהדיסטורשן.
שעושים כאן זה איזשהו אנרגי ואיזשהו D, אז כמה מידע אני יכול להעביר, בהנחה שהמידע כאן עובר בצורה מיידית, שכל הבעיה, נגיד אם לא היה את ה-X, אוקיי, בסדר, חדש לי את ה-C, וזה אתה תסביר לך?
but it's contrast. Yeah, it's going to take me too long. I want you first of all to understand this, and then maybe after. This is not. I'm getting talks about it all the time, but it's not strictly part of this course. Yeah.
We got a little bit lost here. What is this? This B is like a threshold, right?
Yeah.
It's a threshold.
This is the average distortion. So it's a constraint on. It's a constraint on the expected distortion. And where did I write it? Here. So the average distortion means I'm averaging over all W and WH with the right probability.
Yeah.
And I want this average distortion to be less than Z.
This is a function we don't know, right? This is
You know. I mean, you choose it.
I choose it.
I mean, you decide. You tell me what your distortion function. Let's say the square distance, Euclidean distance, or the L1 distance, or the log loss. So there are many possible distortion functions.
Okay.
Actually, I prefer the log loss, as we call it, the KL divergence, which is the right distortion function. But that's so there are many possible choices.
Okay.
For example, in your perception of speech, there are things that you are very sensitive to, and there are other things that you're not sensitive to. So I can be distorted on the kind of things you don't hear. So this is what we call the perceptual distortion. It's actually very complicated. You don't know this function very well, but you can measure it. I can measure in your ear. I mean, to what are you sensitive and what you're not sensitive, and then what you're not sensitive I can distort. It's not going to cost me much. So there is the real biological distortion is really a perceptual function, which is hard to estimate. So in vision, I mean, there are things that we see and there are things that we don't see. So there's no need to be very careful about the things that you don't see and perceive. So I can distort the parts of the picture that you don't really see. That's what we do in JPEG. I mean, essentially, I blur it in many places where you don't really notice it because your perception is limited. So there's a perceptual distortion. After people call even about perceptual entropy, which is really the minimum rate that I need in order to achieve a certain perception. Okay. Now this is very different from a complete lossless recovery of the signal, because we have a very lossy vision. I mean, there are many things I don't see. So if I don't see it, I don't need to transmit them. It's a waste of bits. Okay, so this distortion function is actually a very important thing. I mean, if you can tell me what the distortion function is, you actually understand the problem I'm comes with. So in neuroscience or in cognitive science, we really don't know the distortion functions. So we take things which are easy, like the Euclidean distance, or like the L1 distance, or like the log loss. There are many options. And then, of course, we want to prove theorems about which distortion function is better than another, and so on and so forth. But in general, the distortion function is a tricky thing. For example, in speech recognition, what the distortion function is, the only thing you really care is recovering the text. But if you do speaker recognition, you actually want to identify the person. Now, when we actually talk in cell phones, we want some sort of both. I mean, we want to understand what you're saying, and we also want to identify the person. But if I just do speech recognition, I just want to, speech to text, as we call it. I want to translate it into text, and I don't care about all the features of you. I don't care if it's your voice or her voice. Which means I can ignore a lot of things in the signal which carry your identity and only the text. But if I want to do speaker recognition, I care exactly about the opposite. I want to characterize your identity and not what you say. And so these two type of problems have different distortion functions. So the distortion function is a big black hole. I mean, what is actually behind it? My assumption is that you, as an engineer or as a designer of the system, you have your own distortion function. You know what you want. This is usually the specification of the problem. I mean, for an engineer, communication engineer, give me the distortion function and give me the rate of the channel. And then the rate distortion function is telling me, okay, at this distortion, this is the minimum rate that you need. If you allow more distortion, this is the minimum rate. If you allow less distortion, this is the minimum rate. So this is a translation from the average distortion to the rate. Now, by the way, sometimes people don't care about the average distortion, they care about the worst distortion. I mean, they really want to guarantee not on average, but in the worst case that you're not distorted. Luckily enough, for large problems, this typicality argument tells you that the average and the worst are going to be very similar. So if we are talking about very long blocks, the fluctuations of the tail of the Gaussian tails are going to be small, and the probability of seeing something completely distorted is very small, and that's okay. So it's not really a bound on the worst case, it's a bound on the probability of having very high distortion at some point. So I mean, in our communication, in our video compression, for example, you see it all the time. I mean, see all these glitches of distortion. As long as they're rare, you don't care. The fact that your TV image is actually distorted with respect to the reality, if it's more or less average distortion, you don't really care. I mean, okay, the colors may be not exactly right, and the contours may be not exactly right. As long as it looks natural, you're okay, happy. What you're not happy when I see things which are all these square blocks that really blur the image, and then you know that something went wrong with the code. I mean, this is not supposed to happen. Right.
Is typicality a condition for the existence of distortion function?
Yeah. So as I said, eventually everything is going to be what we call constant rate when you have typical sequences. Everything is going to have a very narrow distribution. And this is again the typicality condition. And then I can actually bound the probability of the non-typical thing. So in the non-typical thing I can have distorted images. Who cares? It's going to have a probability epsilon, okay? And I can push this epsilon to be smaller than 1. So that's the whole trick. I'm actually waiting long enough to achieve, to push everything which is not going to work well to be non-typical. More questions?
Sorry?
Yeah.
Just one more. So, you talk about channel complexity between X and Y, right? But this...
But the distortion between W and X.
Yeah.
That's right. So actually, the distortion is between W and W hat. That's what I really care about.
Okay.
I mean, I want my receiver to have a non-distorted. But my assumption here was that the channel is error correct, which means I separate. I'll repeat it because it's important. I separate the source coding problem from the channel coding problem, and the channel is essentially wrapped with this channel coding, such that from here to here I don't have any noise, as long as I'm under the rate, under the capacity. So this is again one of those Shannon's insights that you can at least asymptotically separate these two problems, the channel coding and source coding. In reality, we don't do this. In biology, we don't do this. In biology, we actually use the noise of the channel as a distortion of the image, or the sound, or whatever it is. And then we do something much more interesting, which is called joint source channel coding. No, I'm not talking about. But if you look at the information theory books, the whole chapter on joint source channel coding, I'm doing a separation. The separation is always possible as long as we allow long delays. I mean, as long as I can asymptotically separate these two problems. I know it's too much for one class, but most of it at the end of the course. And on Wednesday I'm going to talk about simplicity, which is becoming less and less important. I'm happy that I'm spending time on this. The course is short, too short. We need actually 2 semesters of this thing. Eli is not giving it anymore. Yeah.
Why allow larger distortion dynamic of the distortion?
So intuitively, if you have a higher distortion, with less distortion, you can always you need more bits than larger distortion. And why is it monotonically decreasing? So distortion means I see less. So there's some sort of refinement. And from this to here, I need more bits. Okay? Higher resolution. Yeah. So distortion is the resolution. Think about so a very blurry image needs less pixels. Okay. So if you see in JPEG, sometimes they give you these very tiny images, which are if you blur them, if you expand them, you don't see anything. So this is a very highly compressed. So I'm somewhere here. It's very distorted. If I want to see the full resolution, I need more bits. That's obvious. If you want to see a high resolution picture, you need more bits. So that's essentially what it means. I'm climbing that. It's easier, of course, from a high resolution I can get to low resolution. That's easy. from low resolution getting back to high resolution, I need more information.
I wanted to ask, is there a lower bound here as well?
No, of course, if I eventually this goes to zero, this can go asymptotically to zero, or it can go to zero some finite place, and then I don't need any information. If you want maximum distortion, you don't need information. You don't need any rate. All right, I'll talk about it then. Let's call everybody back. All right. So as usual, I got a lot of good questions in during the break, which I want to share with you some of them. So first of all, I emphasize here, and I say it again, that we are talking about what we call separation of the source coding and the channel coding. Can somebody close the door there? So essentially, we assume here that this is called the Shannon separation theorem, that we can error correct the channel independently of the source by wrapping it with the channel coding here and the channel decoding here. This is what we call the error correction. And once this is done, the channel with the error correction is considered lossless or clean, no noise. So this is a very interesting statement. I mean, when can we do it? So strictly speaking, we can do it only asymptotically, when we have very long blocks. So, but this is called the Shannon separation theorem. And then we can do the two things independently. We first compress, even with distortion, and then decompress with distortion. And the channel is just transparent to us, because we already corrected the errors. As I said, I mean, this has a very heavy price. And the price is I need to have very long delays. I mean, I need to encode very long blocks. But in reality, I mean, we communicate in real time, more or less. So there's no channel coding in our communication, at least not explicitly. So this, by the way, is one of the reasons that people think that all this theory is irrelevant for biology, because we usually don't have anything like channel coding in our communication. But it's not true. And the reason it's not true is that there's another version of the theory, which I'm not going to talk about in this course. It's called joint source channel coding, which means I don't break these two blocks into separate blocks. I actually do it together. And in some sense, the noise of the channel is part of my distortion. So as long as the channel is distorting my signals in a way which is not more than the distortion that I'm going to suffer, this theorem is still true. So, and this is how biology really works. I mean, I communicate instantaneously, essentially, with very small delays. And you see, let's say you interpret the word with very small delays. But there are distortions here. There's noise in the channel between us. But the redundancy of my language in this case is precisely compensating for the noise in the channel. So this theorem, the rate distortion function is less than the capacity energy or capacity cost function, is true even when you don't separate. And okay, I gave you many examples in biology how this joint source channel coding is actually happening. Let's say in our auditory system, or in our visual system, or in our any perceptual, any cognitive task. Essentially, we do this type of compression, decompression story all the time. Yes?
When you generalize the channel coding theorem, so the probability should be not different, right?
The rate? Which probability? Oh yeah, so this is generalized to the probability of the distortion being less than d is smaller than some epsilon. And this epsilon should go to 0. So I want this, the probability of, probability is this larger than this is going to be smaller. Or I want most of my communication to have low distortion.
Why larger than is not smaller than?
Because I put epsilon here. So, okay, so smaller than d is going to be larger than 1 minus epsilon. Okay, it's the same thing. I want small probability of having large distortion in my communication. And I want to push this probability to 0. Okay? Now, there's a lot of things here. I mean, this is really just, you know, a very compressed and just the very highlight of information theory. But it's enough for you, I hope, to get some insight what's going on. And if you want to learn more, there are places to do this. There are courses in information theory. There are more courses that I give. There are many things, mainly the books. Read Covell and Thomas. Unfortunately, we have only 13 weeks of course, and I'm trying to squeeze into it a lot of material, which I think is important for LSEC. When I teach machine learning people, I emphasize other things. But that's why I always try to relate it to things that you are really interested in. Okay? Yes?
So is it what you are saying is that in natural language, when we communicate, there is no explicit neither source coding or channel coding because it's via noise, but there is kind of explicit decoding,
Yes.
which is our understanding.
Yeah, actually what happens in biology, it's a very good question, and of course I can give you a whole talk about it. But essentially what happens in biology, what happens through our evolution, is that the channels, the perception of the code itself is adapted to the channels. So let's say that I'm communicating with my language. So usually people talk in a certain noisy environment. This noise has very specific characterizations, like, you know, other people talking in the background, or some noise, you know, what you call natural noise. So there's some natural environment which is giving some natural noise on certain frequencies, and those frequencies, we're not going to rely on the frequencies which are very noisy. So our voice, the way our, let's say, sound encoding, our voice was adapted, was evolved, is by using the frequencies which are less noisy and not the frequencies which are more noisy. So we use very specific frequencies in our communication which are not susceptible to the noise of the environment, and the noise of the environment is more or less universal in some sense. I mean, there's a noise of other people speaking, there is noise of, you know, today we actually, you know, in the modern world we have many different types of noises, machines and airplanes or whatever you want, which really, we're not really adapted to them. But in general, the story was very different in evolution, in biology. It's the channels which are given, and then the nature of the messages was adapted, and the distortion function is adapted to the channel. And that's what we call adaptation. But at the end of the story, we obey channel theorems. I mean, the rate distortion is less than the capacity at a given cost. Now, essentially what happens in biology is that the channel is given. I mean, there are some noises in the environment. Okay, we need to compensate for them. So what we do is we adapt the noise in the channel is precisely related, or is the acceptable distortion. And if it's not, we change the way we communicate. So, you know, when there is a very noisy environment, what we do? We shout. Okay? What do I mean by we shout? We increase the energy in our transmission. And if I had the time, I could show you that this type of communication, the capacity is the log of the signal-to-noise ratio, or log of 1 plus the signal-to-noise ratio. This is what we call the Gaussian channel. So by increasing the signal-to-noise ratio, you actually increase the capacity of the channel. Okay, that's nice. So that's a very nice way of adapting. There's noise, shout. Okay, it's a very natural thing. We do it all the time. Yes?
When you shout, you change anything in the rate, or it's only about the...
Of course, we actually increase the capacity.
But if
So this capacity is essentially the log of 1 plus the SNR, the signal-to-noise ratio, which you don't know what it is, but you know what it is. Not for me, but so signal-to-noise ratio is essentially what is the energy of the signal compared to the energy of the noise. So if you want to keep the capacity constant, we must increase the signal-to-noise ratio to keep the same capacity. And that's what we do when we shout. So shouting or putting more energy in some sort of an encoding, yeah, I'm actually giving you better capacity. If you're quiet, like now. And I can talk softly and spend less energy. And actually, I do it without noticing. I mean, I adapt my communication to the channel. And this is happening at all levels everywhere. The channels, the distortion of the communication is adapted to the existing channels. And we actually select the channels such that we can communicate well. Yeah. Right.
But the capacity is property of the channel, not of the source.
Remember that in order to communicate, I need the rate to be less than the capacity. That's a very basic law of nature. This one. Now, without this, I cannot communicate. That's what Shannon told us. There's also, as I said, a converse theorem. If I'm communicating above the capacity, I'm not going to understand it. Now, this communication happens on all levels, not only on the level of the voice. It happens on the rate of the messages. It happens on, if I see that they don't understand, see too many eyes that look at me as if I'm speaking Chinese. No, Chinese that people understand here, but since speaking something you don't understand, and then I reduce the rate of ideas per second. I essentially speak slow, try to explain things. This is, again, an adaptation.
But it is the source which is changing.
That's right. So I change both the source and the distortion. I mean, I'm changing the rate of entropy, and I'm adapting to the distortion level in the sense that, let's say, there are things that I know that you don't know. Yeah. I'm not going to use the mathematics that you don't know, because this is above your distortion function. Right. Okay?
How is it updating the shock?
It's the energy. It's here. I increase the energy of my voice. It's just essentially multiplying. It's a very simple source coding. You're right, but it's a source coding.
The source doesn't change.
In this case, the source didn't change. But let's say that I adapt to, I see that there is a branch of mathematics you never heard of. I'm not going to use it. So this is adapting the source. It's adapting to the distortion and so on. So all these kind of things are some sort of adaptation. Okay.
So adapting the distortion means like how much am I willing to
the distortion is a function of the thing that you are sensitive to or not. So for example, if you compress an image, there are things that you don't perceive. This is what we call the perceptual entropy. So there are changes in the image. Let's say I take this image. There are many, many things that I can change here and you will not notice. It will look exactly the same to you until you really overlap them. And so I can use this type of distorted things to save bits. So the distortion function depends on what it is that you care about and you're sensitive to. And if I notice that there are things that you care about more than others, I'm not going to distort the things that you care about, and I am going to distort things you don't care about. So this is exactly the adaptation that biology is doing all the time. Now, we can talk about it forever. I really want to say something. So again, now we have two functions. We have the rate distortion function, which goes like this, and we have the capacity cost function, which looks like this, more or less. So this is going to decrease with the rate, and this is going to increase with the cost, with the energy, let's say. Okay? So now the engineer usually has this problem. I mean, I want the minimum energy at a given distortion, or the minimum distortion at a given energy. This is the physical trade-off. I want to communicate with the smallest possible energy at a given distortion level. So what should I do? So let's say this is the energy that I want to be here. So I look at the capacity. This is the maximum capacity I can achieve. Okay, now I go here, because remember, C and R have the same units. It's rates, bits per second. So now I go here. Oh, so this is the minimal rate that I need. And therefore, this is the distortion I'm going to suffer. So I do this type of combining these two things together. If you have more energy, I can have lower rate. If you have if you want lower distortion, you need more energy. It's the same. Okay, so you tell me usually it goes that way. I mean, you tell me what the distortion you're willing to suffer, what is the accessible distortion, and I'll tell you what is the minimum cost, minimum energy that you need to pay. Okay? So these two functions are really the whole story. If I know the cost capacity function and I know the rate distortion function, I can solve the physical communication. Yes?
What function transfers you from this? How do
How do I know? So I mean, the condition of communication was this. The rate must be lower than the capacity. So I know, so you tell me what is the distortion, this is the minimum rate. This must be lower than this number, which means this is the minimum energy. You have a minimum cost. If you give me, this is the cost, yeah? Cost and distortion. So this is the average distortion. So essentially, there's the trade-off. This is the trade-offs, and this trade-off is completely controlled by these two functions. Okay. So usually, by the way, this goes. Let's say for Gaussian channels, this goes like exponentially decaying. This increases logarithmically, like this. What I said here, log of 1 over s and r. But in other channels, it looks very different. Yes.
Some units, so the rate in bits, but
These are always bits per second. These are always information per unit time, okay? Bits per second, both here and here. You're right, I mean, I have to work in the same unit. Otherwise, I can't compare. But this can have very different things. This can be energy in joules per second, in watts, let's say, and this can be distortion in dB of distortion or whatever your distortion measure is. D and E can have very different dimensions. So the real trick of information theory is that you take this physical problem. If I ask you what is the connection between the energy or the cost of the communication and the distortion, this is a very tough problem in general. I need to know the physics of the communication. I need to know the physics of the channel. But if I translate it to information to this axis, it becomes very simple. Just compare the capacity with the rate of the channel. Okay, so now I want to give you the intuition behind the two theorems. So this is called the rate distortion theorem, or RDT, rate distortion theory, and this is called the channel coding, or the channel coding at a given cost, the error correcting. So surprisingly, actually if you look deeper into it, you see it's not so surprising. These two problems, the compression with distortion and error correcting with certain cost, are dual to each other. There are two sides of the same coin. So by the way, not the way usually information theorists like to teach it in traditional information theory courses. They completely separate these two problems, and there's a branch of information code theory which people who are doing source coding or data compression, and there's another branch of people who hardly talk to each other who are doing channel coding. This is really ridiculous. It's just like linguists. Some of them doing morphology and some of them doing syntax. And they don't talk to each other, as if there is no connection between the two. It's of course completely, it doesn't make any sense. But that's what happens. Some of them are doing semantics and some of them are doing syntax, okay, whatever. So these two problems are highly related to each other. Now, what is the intuition? So why is it that the capacity, which is defined here as the maximum information between x and y, is precisely the rate that allow me to communicate without errors? How are these two things related? Okay, so this is really I need another piece of board. Sorry? So the rate distortion problem, I mean compression with a given distortion, and the channel coding problem, which is communication with no errors. And from what I told you, you can already see why they are dual to each other. Because in one case, I'm trying to compress at a certain level. In the other case, I'm trying to recover errors, which are some sort of distortion. So there is some the intuition that these two things are related is surfacing when you think about it. But these two problems, which looks very different. I mean, this was a source coding compression problem, and this was an error correcting problem. What's the connection? Okay, so I'll show you what the connection. So imagine now that my messages live in this space W. What I mean by that circle is that every point in this set is a different message. Okay? So every message, this is message 1, this is message 2, and so on. This is message 3. So every point here is this message, and I already know that the volume, the number of messages here is what? but the number of typical messages there. Okay, there may be non-typical things. And the non-typical things are those sentences that don't make any sense, or those things that you don't care, or those images that don't look like anything you want to recognize, or things like this. Okay, these are the typical, non-typical things. But what is the main essence of typicality? So we know that the size of this set is what? Is 2 to the entropy of W. So the number of different typical instances there is essentially, they're all equally likely in this asymptotic sense, and they all have probability, which is 2 to the minus n entropy, minus 2 to the minus entropy. There's an n here, which I need to put, which is the number of messages I'm coding together. So this is the entropy rate, and this is the number of blocks or number of messages I'm throwing together.
Each W is a sequence of...
So now, when I wrote n here, each W is a sequence of n messages. Yeah. Okay, but that's, let's keep it aside. I don't want to confuse you too much. Okay? Now, let's say that this W is now encoded. So I have the X, I have the Y. So let's put W aside for a second. I'm now working within this separation framework. And this X and Y are related through the channel probability distribution. By the way, I didn't really give you any example of a channel. So actually, I gave it last time. So the simplest possible channel you can imagine is what we call the binary symmetric channel. So if X is bits and Y is also bits, 1 bit, and that's they move with probability 1p here and probability 1 minus p. They are confused. So which means that this probability distribution is p, 1 minus p, 1 minus p, p. This is the p x given y given x. Okay? So in this case, what is the channel capacity? Okay, we can calculate it. Straightforward exercise. This is simply age of y minus age of y given x. And age of y given x is simply the entropy age of p, as you can easily see. The binary entropy of p. So it's the for both of them, both of this is age of p, both here and here. So it's just age of p for both y's. And the maximum entropy that I can have in y is 1 bit. So the capacity is indeed 1 minus age of p. This is very easy to, it's an easy exercise. Okay, so this is called the binary symmetric channel, BCS. This is the simplest and the standard example. If you don't understand anything in information theory, just like the spin half is the canonical example in physics, in quantum mechanics, and the binary symmetric channel is the canonical example in information theory. Okay? So of course, when is the capacity 0 in the binary symmetric channel? No, if p is 1 or 0, then it's the maximum capacity. Then I have no noise. So when is it going to be randomized?
So why is it independent?
Yeah, when it depends on phase, that's right. But what is p? Half. Yeah. Okay. I wanted all of you to say it together, but it didn't work. Okay. So 1/2. When p is 1/2, the HP is 1, and the capacity is 0. Okay. So again, p 1/2 means that for probability half I give you 0, and for probability half I give you 1. So there's no correlation. I mean, in that case, x and y are independent. No. So okay, that's a very natural, a very intuitive thing. But as long as p is not half, there is a finite capacity. And which means there is something I can send you. And eventually I can communicate with no errors. Okay, so now how does this work? So essentially, let's say that now I'm encoding the W by what I call source coding. So I'm actually sending each W to a sequence of X. So which means that this W1 is going to be encoded by some sequence here, and this W2 is going to be... What's here is some sort of a tree, or a prefix tree. So essentially, for each W, I encode it by a sequence of bits. Let's say. Okay? So that's what we called source coding. Okay? Or compression. Like all those trees that I showed you. I mean, we know how to do it. So there is some sort of a one-to-one or uniquely decodable code. Each one of those messages is going to be encoded here. Okay? But now, there is this noisy channel here. So it's going to take this sequence of bits, which are the code of one of the W's. So let's say W1 is encoded by X1, and W2 is encoded by X2, and so on. So this is a sequence of n bits. Okay, so it's not exactly this n, it's another n, but this is the n of the length of the code. So remember, if let's say W's are words, and the sequence of bits is a sequence of bits, then the length is different. Yeah? Okay, I can have, let's say, 10 words, I need 1,000 bits to encode, or something like this, 100 bits to encode. So this is the length of the code, but of course the rates are such that this n determines the rate here.
So the lower index in X and W are the same, but the upper index is the compression.
Yeah, so yeah, that's right. So I compress, now I'm talking about the length of the code, so there's another conversion of units here. I'm moving from messages to bits. But that's, so, and of course the average number of bits is the average length of the code. This is what we proved is bounded by the entropy. Okay? So now I'm talking about bits here. Okay? Now each of these bit sequences, imagine, let's just for simplicity, that these are bits, and this is a binary symmetric channel. Okay? So what's going to happen? Each bit has a probability p, a 1 minus p, to being confused, to being inverted. So my sequence is going to be received on the other side by many possible sequences. All those flipped bits. Okay? So let's say I send 1, 1. So there's a probability that is received as 1, 1, which is p squared. And there's a probability it is received 0, 0, which is 1 minus p, 1 minus p. And there's a probability of received 1, 0, 0, 1, which is 1 minus p times p. Okay? So all these possible sequences can happen. What it means is that I send one sequence here, and this sequence is blew up to many sequences. Okay? So remember this. So the noise in the channel is going to blow my transmitted message to a cloud of possible sequences. Okay, that sounds bad. All of the messages are confused with each other. So what should I do in order to actually not confuse them? Yeah, that's right. It's a very simple idea. So this is in the Y space. This was the X space. This is the X and whatever. They are the Y space. In the binary symmetric case, these are bits and these are bits. But I emphasize again, they don't have to be. This can be words and this can be spikes. I don't care. But there's some conversion between them. So in this particular case, every sequence here is blown to another sequence. Okay? So as Noga told us, I mean, in order to actually have uniquely decodable code here, or error correcting code, I need those spheres to non-overlap. Okay, this is blown to this, and this is blown to this. As long as these things are not overlapping with high probability, that's a probabilistic thing, I'm going to be fine asymptotically. Okay, but what do I know? So just as I knew that the volume of this is 2 to the n age of x, the volume of this is 2 to the n age of y. What is this volume? What is the typical volume of the expanded sphere? That's right. Okay. So this volume is precisely 2 to the n age y given x. Why? Because this is a typical sequence of the conditional probability. And again, I'm using the same typicality argument. So I conditioned on a given x here, and I assume independent. That's why I wrote it like this. It's all right. I didn't assume independent. I just assumed this is the entropy rate. So this is why I have the n here. So this is going to be blown up to a typical sequence of this size. Okay, so what is the maximum number of non-overlapping spheres that I can have here? What is it?
Total volume divided by.
Yeah, it's so the maximum number of non-overlapping is precisely 2 to the n hy, which is the total volume, divided by 2 to the n hy given x. Now that's it. This is the idea. What is it? It's 2 to the ni. Because I is exactly hy minus hy given x. Okay? This is really why I is so important. Because it's really counting the number of non-overlapping spheres here. So as long as my rate, which means the number of spheres I'm actually sending, is separated, they don't overlap with high probability, I'm okay. I can correct the errors. Because all the errors that happen to this, all these sequences are different from these sequences and different from these sequences with high probability. Are significantly different, and I can actually separate them by some sort of an hypothesis testing. That's what we do here. Eventually, we do an M-Pearson type of thing in the decoding. Yeah?
How do you make sure they don't overlap?
So this is the way I construct the code. So the error correcting code is precisely how to make sure that these don't overlap. But even without telling you the code, I can tell you that the maximum number of elements that you can separate is this. Because if this is the maximum packing, the highest packing that I can do of non-overlapping spheres. So this is what we call sometimes sphere packing problem. What is the maximum number of spheres that I can pack in this volume? Okay? So this is the source coding intuition. It's not really it's the essence of the proof, but it's not the proof yet. I need to put it in a formal way, which I don't have time to. Yes?
To the nhy or hx is it the number of objects or is it the volume of
it's the volume of sequences here. So remember, this was the number of typical sequences here.
So
this is the number of typical sequences here, and this is how much each one of them is going to be blown by the noise. The noise is blurring it. Now, if it's a completely random noise, what's going to happen? That all those are going to be blurred to everything. Zero capacity. I cannot distinguish anything. But since it's not completely random, different words are going to be just distorted a little bit. So let's say the simplest possible error correcting code is simply repeat your message, let's say 3 times. Now, if the probability of flipping a bit is smaller than 1/3, so the 0, 0, 0 is 0, and the 1, 1, 1 is 1, and the probability that the majority is mixed is very small. So the simplest error correcting code is what we call the repetition code. If you repeat sufficiently many times, eventually you will be able to separate, because the probability that a sequence of long sequence of zeros and long sequence of ones will be confused with each other is very small. Okay, so this is essentially the probability that a coin flip all ones and a coin flip all 0 give me a sequence which I cannot separate. But of course I can separate if the noise is small enough. This is just a typical a likelihood ratio test, because I have different source, I have different hypotheses, and the likelihood ratio or the log likelihood ratio test is going to separate. Okay, so I'm not going to talk about it, but you already see that the decoding is some sort of an hypothesis testing. I need to decide if the sequences that I see here belongs to this hypothesis or this hypothesis. So that's how these two problems are very closely related to each other. Okay, so of course, as you said, I mean, how do I code? So this is an art, or a completely different subject, how to construct efficient error correcting codes. And you know, mathematicians invented all sorts of number theoretic schemes which are very, very intelligent. For example, parity. So let's say that I assume that there's only one mistake in every 10 bits. This is something, it's an assumption about the code. So the probability of having 2 bits false inverted in let's say a sequence of 8 bits is very small. So I assume that I don't care about. So I send just one more bit, which is the parity bit, which is the XOR of all the bits. And if this parity, if there's one error there, this parity bit is going to tell me there was an error in your word, in your 8 bits. So a parity code tells me it's not correcting the code, it's just telling me there was a mistake in this word, send it again. So this is how error correcting, how parity check works. But I can do something much more clever. I can send 2 or 3 bits, which will identify where the errors are. So these are number theoretic ideas, very nice, very sophisticated ideas, which I'm not going to discuss here, which is called coding theory. How can you correct some of those bits with all sorts of tricks? So I can have enough equations in some way that allow me to actually identify which bits were corrupted during this communication. So this is a complete different type of art, which is really a lot of number theory and a lot of very interesting things there. How do you correct code? How you construct error correcting codes? But Shannon already told us that this is the limit. Yeah, you cannot go beyond it. Okay, so what's happening on the other side, the rate distortion problem? So I just want to convince you that it's essentially the same type of problem. I have 5 minutes for this. Okay. So what happens in the rate distortion? The rate distortion, to see that these are dual problems, it's a bit tricky. But I'll try to use the same pictures again. Yeah, almost the same picture. So essentially what I do is I'm trying to, now this is my words. Okay, let me erase. Now I'm allowing some sort of distortion. So let's call this W hat. So let's say W2 is now, if I allow some sort of distortion, it means that I'm actually willing to see not the exact W, but some small distorted image of it. So now this space is the space of all the W's, W hat, such that the distortion between